In the previous video, I discussed how computer memory is used by a program to read and write information stored as bit patterns at certain addresses. And I briefly introduced the concept that there are different types of data, some of which need more than just one byte to represent them. But I didn't elaborate on that. In this video, I'll go into more detail about those different data types and how they are represented. The C programming language gives you the ability to define contiguous blocks of memory that can be used to store and process data. Each of these memory blocks will have an associated single address that can be used to locate the block and access its values. This address will be the address of the first byte in the block. Because it's unintuitive to a person to refer to each block of memory by a simple address number, C allows you to associate a more human-friendly textual label to each such block of memory. In your source code program, you will usually refer to each such memory block using that name label instead of its address. These blocks of memory that you can define and name in this way are of two main types: functions and variables. Functions are memory blocks where the bit patterns stored represent both data and instructions that define processes to perform on or with that data. If you refer back to my first video, this equates to a collection of both operands, the data, and opcodes, the instructions. Variables are memory blocks used to store values only. These values may change as your program progresses, but the memory block of a variable only acts as a store for the value. Unlike a function, it does not contain any processing instructions for manipulating the value. It's important to emphasize that both functions and variables are simply blocks of memory that contain some bit pattern data and that have an address that define the beginning of the memory block. The name that you allocate to each of these types of memory block is up to you, but there are some rules and exceptions that limit what names you can give. For example, names cannot begin with a number, and they may only use letters, digits, and underscores. They cannot contain any spaces or other characters, and they must not be identical to reserved key words of the C programming language, such as goto, or int, or else, etc. Also, names are case-sensitive. It's also important to note that these names are purely for your ease of programming. After the source code is compiled, the machine code executable version of your program will only implement the addresses for your functions and variables. So, you will not gain any speed or efficiency by using short names instead of long names. In the rest of this video, I'll be discussing only simple single variables. Functions will be covered in more detail in another video. There are also types of variables that are combinations of single variables, called arrays, structures, and unions, and again, these will be discussed in other tutorials. So, a variable is a block of memory that is used to store some value. In the computer, this value must be stored as a binary bit pattern occupying one or more bytes worth of memory space. But you don't want to use more bytes than you need for the job, because memory is a finite resource. So, what is the minimum number of bytes that a memory block must contain, and what format or rules for arranging these bits should we use to store a particular value? Well, the answer to those questions will be determined by the type of data that is to be held in the variable. A small integer might be represented by 1 byte, with the bits arranged according to the usual binary counting format I described in the previous video. Using that standard binary counting format, 1 byte can represent the numbers 0 to 255. But this won't work for positive integers larger than 255, or negative numbers, or numbers with fractional decimal places. So, if every type of data can't be stored as a single byte in standard binary counting format, we need some way of letting the compiler know what type of data is going to be stored by a variable right at the start, so the compiler can allocate the correct amount of memory space to hold that type of data. And, when we actually come to reading or writing some data in that variable's memory block, the computer will use the correct bit pattern storage format so the value will be represented correctly as intended by us. The way in which we let the compiler know this information is by specifying a quality called a data type whenever we first declare any variable in our program. The data type is specified by one of the key words shown in the table. We don't use the word pointer directly, which is why it's in brackets. I'll explain more about that in another tutorial. There are some variations or qualifiers that we can add to those data types, and I'll discuss those as we go along. If you choose the wrong data type for storing or manipulating information, for example, if you declare a variable as an integer data type and then you try to store or manipulate fractional numbers using that variable, your program will not give the correct results. So, it's important to understand what these data types mean. The smallest data type in C is called the char, which is short for character for reasons I'll mention later. A char is defined to be exactly 8 bits long, that is, 1 byte. We've seen from the previous video that a string of 8 bits can store 256 different binary states. But remember, the meaning of those states, what information they represent, is up to us to define. They have no intrinsic meaning to the computer. Now, one possible way we could use those 256 states is simply to represent the integer numbers from 0, where all 8 bits are set to 0, all the way through to 255, where all 8 bits are set to 1, by simply counting in the binary number system using all 8 bits for the count. But what if we need to represent negative numbers? What convention or rules of formatting the bits can we come up with that will allow us to do this? Over the years, a number of different ways have been tried. A very simple rule for expressing negative numbers in binary is called the signed magnitude method. With this method, we reserve one bit to be a sign indicator bit. By convention, the sign bit is chosen as the leftmost bit. That is, the bit that would have represented the highest power of 2 in a normal binary number. We call that the most significant bit, or just the MSB for short. Because we're using this bit solely as a sign indicator, this bit is no longer able to participate in the binary counting patterns. So, when using this method with a byte, for counting purposes we only have 7 bits, so we can only count from 0 to 127. But now we can define a number to be negative if the sign bit is 1, and positive if the sign bit is 0. So, for example, this pattern would represent the integer 78, and this pattern would represent the integer minus 78. Now, that simple signed magnitude bit format works for individual numbers, but we run into a problem when using it for general arithmetic. For example, let us add the number 25 to minus 25 using this signed magnitude representation. In this first column, 1 plus 1 is 2, so we put a 0 here and carry 1. In the next column, 0 plus 0 is 0, but we also add the 1 we carried over, so the final result here is 1. 0 plus 0 is 0, 1 plus 1 is 2, so we put a 0 and carry 1. 1 plus 1 is 2, so we carry 1, and we would have put a 0 here, but we have to add the 1 we carried from the previous column, so we put a 1 here. 0 plus 1 is 1, 0 plus 0 is 0, and so we get to the sign bit. So if we just do binary addition as normal, we get 0 plus 1 is 1. This gives an answer of minus 50, which is clearly wrong. If we didn't do this addition on the sign bit, then it would still be plus 50, and that's also wrong. So, to get the right answer when adding a negative number to a positive number, we would need to invent some complex special rules that make exceptions when we see a sign bit. This can be done, but it's a lot of extra computation, especially when you want to add many hundreds or millions of numbers, some of which may be positive and some negative. Another problem with the signed magnitude format is that because we use the most significant bit solely as a sign indicator, we are not using the full range of 256 possible values that a single byte can offer us. Instead, we have 255 values, that is 127 positive values, 127 negative values, plus 0. Also, 0 can be indicated as positive or negative. Positive and negative mean nothing when it comes to 0, so this tells us that we have redundant, useless information when using this signed magnitude format. So, is there a better way? Yes. A more efficient format for expressing signed numbers in binary is the so-called 2's complement. The 2's complement method is not simply a format for representing a negative number. Instead, it is a procedure for negating or inverting any binary integer. That is, for multiplying any binary integer, whether positive or negative, by -1, thereby flipping its sign. Furthermore, the 2's complement procedure doesn't use the most significant bit as only a sign bit, thereby preventing it from being used for anything else, as with the signed magnitude method, but rather it uses the MSB as both a sign indicator and a value bit simultaneously. In this way, the 2's complement can express negative numbers while still expressing the full range of different values available with any given number of bits. So, what is this amazing procedure? Well, the procedure itself is very simple. Starting with any binary integer, you do the following. 1. Invert all the bits, and 2. Add 1 to the result, and ignore any carryover that may occur from the MSB. So, how do we use this method to represent negative integers? Well, we simply define the 2's complement of a normal or positive binary integer to be the negative version of that integer, even though in most cases it looks quite different to the positive version. However, this definition is not arbitrary, as you'll soon see. Note that in the 2's complement of any positive binary number, the MSB will be 1. For this reason, all negative numbers represented in the 2's complement notation will have an MSB value of 1, just like our signed magnitude numbers. But, unlike the signed magnitude method, the rest of the bits will also be altered compared to the positive version of the same number. Note that applying the 2's complement over and over to the same starting point number simply alternates between the usual binary representation, which we would call positive, and the 2's complement, which we define as the negative version of the same value. So applying the 2's complement method behaves just like multiplication by -1. Now, what happens if we take 2's complement of 0? Do we get some meaningless negative 0? Well, let's see. First, invert the bits, then add 1. Because all the inverted bits are 1, when we add 1, we get a flip back to 0 in each column with a carryover to the next column, until right at the end we also get a carryover, but by the rules of 2's complement, we simply drop the final carryover to leave just the 0. So, the 2's complement of 0 is just 0. The MSB is also 0, so there is nothing negative about it. Now, let's do some 2's complement addition. Let's add +25 to -25. You do this using ordinary binary addition. There's nothing special about the addition process, and there's no need to exclude the value of the MSB or test for it and branch off into a special procedure or anything like that. Just plain binary addition that you would do with any 2 binary numbers. The only special thing here is that the negative number, our -25, is represented in 2's complement notation, and any result we get must also be interpreted as a 2's complement value. So, doing the addition, we see that we get 0, which is what we expect. But what about a subtraction that will result in a negative number? For example, 115 minus 127, which we know should give -12. Let's see if it works with 2's complement. First, let us find out what -127 is, starting from +127 and applying 2's complement like so. First, invert the bits, then add 1. So, this is -127 in 2's complement notation. Now we do simple binary addition to 115, as shown. You see, the result is something with a 1 in the MSB. So we know this must be a negative number because we're interpreting all results in 2's complement. But what is this negative number? There are 2 ways for us to figure out the value of a 2's complement negative number in decimal notation. One way is to apply 2's complement to it, because this will flip the negative number into its positive equivalent, as we have seen before. So, first invert the bits, then add 1. And we get the answer 12. So, the 2's complement we got this from must be -12, which is the correct answer for 115 minus 127. The second way to get the value of a negative 2's complement number is to convert directly back into decimal by recognizing the fact that the MSB encodes value as well as sign. So, without 2's complement, the MSB here would be 2 to the power of 7, or 128. Because we are dealing with 2's complement, however, we make this minus 128. With this insight, we simply add minus 128 to the other on bits, which here are 64, 32, 16, and 4. And we get the same answer, minus 12. So, with 2's complement using 1 byte, we can represent all values from -128 to +127. And if we include 0, that comes to the full 256 different values that are possible with 8 bits, as opposed to the 255 values you can represent using the simple signed magnitude method. It is for these reasons, ease of arithmetic and full use of all bits for value information, that all modern computers use 2's complement to represent negative integers in binary. Also note that all the range of positive values and 0 give exactly the same bit pattern across all the bits, whether using ordinary binary or 2's complement. They differ only once you reach the midway point, which, for a single byte, is 128 and above. So now you can see that this bit pattern here can mean 2 different values. If interpreted in simple binary, it has the value 175. But if interpreted in 2's complement, it has the value -81. So, if this binary pattern shows up in some process, how does the computer know which of these 2 values to treat or display it as? The answer is, of course, it doesn't, not unless you specify to the computer which notation is being used beforehand. That's why when specifying some integer value in C, it's not enough to just specify how many bytes that value can use, for example the char meaning 1 byte, but you also need to qualify this specification with a statement of signedness, that is, whether it is a signed char, in which case the value will be able to range from -128 to +127, and the computer will use 2's complement conventions in dealing with it, or an unsigned char, in which case the computer will treat this value as a plain byte to be interpreted without 2's complement, and so it can take on the values 0 to 255. For the integer data types discussed in the following section, a C compiler will interpret them as signed, unless you use the unsigned qualifier. However, for char the situation is special, in that some compilers on some processor architectures will interpret char on its own as unsigned. That is, the default rules for signedness of the char are implementation dependent. Therefore, it's good programming practice to always use the signed or unsigned qualifier when specifying some value as being of the char data type in C. For example, in a C program, if you want to declare a variable that can hold a maximum of 256 different integer values, you can do it as shown. The char data type gets its name from character because an old standard for representing alphanumeric characters used a conversion table that translated each character to a number, and these numbers would typically fit into the range 0 to 127, or, if extended characters were used, such as simple graphics, 0 to 255. So a single byte could be used to represent any of these characters. A common standard still used today is the American Standard Code for Information Interchange, or ASCII, and the illustration shows the ASCII table of characters and their numerical equivalents. Nowadays, the ASCII code set is subsumed into a more modern system of representing characters called UNICODE, but this is beyond the scope of this tutorial. We've seen that the char data type can be used to store integers in the ranges -128 to +127, or 0 to 255. But what if you need to represent an integer larger than that? Well, for those values, you need a data type that is more than 1 byte long. C provides several such data types, which are variants of a basic data type called the int, which is short for integer. These variants are the short int, the long int, and the long int. All, apart from the plain int, can be used without the word int at the end, so you'll see some programs using them as short, int, long, and long. The number of bytes each of these uses is implementation dependent, but typical values would be as shown in the table. There is a signed and unsigned version of each, but if you don't provide a signedness qualifier, the compiler will assume it is signed. This is a more consistent rule as opposed to the situation with the char. The binary representation of numbers in these ints is as described for the char, using 2's complement for signed types. A 2 bytes integer, that is a short int, will be capable of representing 2 to the power 16, that is 65,536, different values, and these will be either unsigned integers from 0 to 65,535 for the unsigned short, or a signed short would have a range of minus 32,768 to positive 32,767. Similarly, the other types of integer will represent 2 to the n different integers, where n is the number of bits, not bytes, it provides. So far, we've only considered data types that represent whole integer numbers. But how can we represent numbers that have some fractional decimal component like this, using a fixed number of bits? For example, let's say we have 16 bits or 2 bytes. How can we use them to store such numbers? Well, an obvious, simple solution would be to use a fixed number of bits, let's say 1 byte, to represent the number that comes before the decimal point, and a fixed number of bits to represent the number that comes after the decimal point. This kind of data type format is called a fixed point representation, because the decimal point can't move to different positions in the string of bits. This works, but just as using the simple signed magnitude method for integers was shown to be inefficient and 2's complement was better in many ways, so also using this fixed point representation has several disadvantages. One of them is that you greatly limit the absolute range of numbers you can represent, and you fix the precision, that is the number of decimal places, to a constant range. For these reasons, most computers use a floating point format, which uses a fixed number of bits for the main numerals, called the mantissa or significand, and a fixed number of bits for a power of 2 multiplier or exponent value, which encapsulates standard scientific number notation. The value in the exponent determines where the decimal point should be in the mantissa. A big advantage of this is that it allows you to represent a larger total range of numbers at the expense of a variable number of decimal places precision across the range. The most commonly used floating point format today is the one defined by the IEEE 754 standard. The details of the IEEE 754 system are beyond the scope of this video, but I'll put a link to a more detailed explanation of it in the video description below. C has the floating point data types shown in the table that vary in the number of bytes they use and therefore the maximum range and precision of values they can represent. A few practical points to bear in mind when using floating point data types are: 1. Unlike with integer data types, you cannot omit the word double after long, because otherwise the compiler will assume it is a long int. 2. There is no signedness qualifier for floats and doubles, because the IEEE 754 standard inherently represents both positive and negative numbers. And 3. All floating point representations use a finite number of bits, so the level of precision will also be finite. This means there will inevitably be some degree of rounding off or truncation of long decimal fractions during any calculation. For this reason, especially if you're going to do multiple calculations in your program, it's better to use the longer double precision floating point formats, that is double or long double, rather than the simple float. In summary, a variable is a block of memory you can address using a custom name, and which stores a value in a particular format called a data type. Each data type has a characteristic size in bytes and format for interpreting binary values. Negative values are represented using the 2's complement binary inversion procedure. Fractional numbers are represented using the IEEE 754 floating point format. Floating point values have the potential for round-off errors due to the finite number of bits used to store them. If you like this video, please hit the thumbs up like button and view some of the other videos on my channel. If you'd like to support the project, you can do that by subscribing to this channel and telling others about it. If you'd like to help me continue this work, take a look at my Patreon page, where you'll find additional content and early bird access to future videos. Thanks for watching.